Hi and welcome to Unit 2, Topic 1, Video 4, where we talk about the polar form of a complex number. So in this video, I'm going to go through some examples and just show you how to convert a complex number into polar form. In later videos, particularly de Moivre's theorem, we'll see why this is so important and what it can do for us. But for now, just know that it's exactly like our work in vectors, almost exactly like our work in vectors. So a little diagram here. I've got my little cast component because we need to consider that, and you've done some of this work in methods. And then we've got a coordinate a comma b. So a comma b is the complex number z equals a plus bi, because we've got a real axis and an imaginary axis in an Argand diagram, as you've seen in the previous video. Now, if I draw a triangle out to that point, I could write my complex number in polar form by writing it in a form that represents theta and r instead. Now you remember, of course, that when we did this in vectors, we would just simply calculate theta and r and put them into a paired bracket like a coordinate, and that would be our representation. It's a little bit different for complex numbers. Not a lot different, but a little bit different. So let's have a look. First is this recognition that the real component z is equal to a, and we know that cos theta is equal to a over r. Just have a look at the diagram. And that means that a, the real component, is equal to r cos theta. The imaginary component is b, and sine theta is equal to b over r. So the imaginary component has b equals r sine theta. Now this leads us to this concept here, which is that z is equal to a plus bi, which now is equal to r cos theta plus I times r sine theta, and that's equal to r cos theta plus I sine theta. And we write that as, I've left myself very little room, we write that as r cis theta. So r is called the modulus, sometimes written as mod z, and theta is called the argument, sometimes written as arg z. And if we can calculate our modulus and argument, then we can write a plus bi instead as r cis theta. And r cis theta is just a simpler version of r cos theta plus I sine theta, and you can now see where that comes from. So we just have to calculate r and theta. And to calculate r and theta, we do go back to traditional methods. But we have to be careful, which is why I've got my cast diagram here. So we can calculate theta by either doing what I've just done here. Cos theta is a over r, sine theta is b over r, but we have to calculate r first using Pythagoras' theorem. Or we could just do it using the old tan inverse equals b over a. But in any case, we have to be careful that we are quadrant aware. So we're thoughtful about which quadrant we're in. We make sure that our argument is in the right quadrant. R, on the other hand, is just a distance-based idea, so it has to be the positive value. So it'll always just be a Pythagorean calculation. So let's have a look at some examples. A, express z plus equals 2 plus 3i in polar form. So to do this, I'm going to start by calculating my r and my theta. R is equal to the square root of 2 squared plus 3 squared. That's what this is going to look like, and just keep in mind, I can draw the diagram if I want to. So 2 plus 3i is here, that's theta, that's r, and my triangle has a height of 3, that's the imaginary component, and a length of 2, a base of 2. So r is equal to that, which is equal to the square root of 13. And then I'm going to calculate my argument. Theta is tan inverse of b over a, and I'm being quadrant aware, and in this case being quadrant aware tells me that my tan inverse of b over a is in the first quadrant, and so it'll be the first answer I get out of my calculator. And this will be a calculator answer, mind you, so I'll need to quickly do this on the calculator to get my answer. Now I'll just write in what it's equal to, tan inverse of 3 over 2, and tan inverse of 3 over 2 is equal to 0.98 radians, or I could write it down as 56.31 degrees. And we're going to really move towards that concept of using degrees less and less often and heading towards radians. So you've seen that now in methods, and we're kind of expecting it now in your complex numbers work. Okay, so that's A and B. So that's A. Now we're going to look at B. And B is transforming it the other way. So if we know that Z is equal to 3 cis, and of course I haven't actually finished A, so I should write down an A now. I'll just give myself a touch more space. A, Z now equals root 13 cis 0.98. That's my final answer. In B, Z is equal to 3 cis 4 pi on 3. I can evaluate this just by expanding. This is 3 cos 4 pi on 3 plus I sine 4 pi on 3. Now I just want to do my quadrant thing. Over here is pi. That's 3 pi on 3. So 4 pi on 3 is down here. And that's pi on 3. Go back to your work on methods if you're unsure about that. Now I can translate that into the first quadrant here. But sine and cos are negative. So that means that this is equal to 3 negative cos of pi on 3, which is 60 degrees, plus I sine, and it becomes, or actually I'll do plus I sine times negative sine of pi on 3. This becomes 3 times negative a half, cos of 60 is a half, minus root 3 on 2 I, and then I expand it out as negative 3 on 2 minus 3 root 3 on 2i. And you can see that's about here. It's got a distance of 3, and that makes sense. Okay, so there's our first two examples. Hopefully they make sense. Now, I just want to show you something here. This is a bit of a tricky one to show you because year on year I'm going to change the order of things. And so for some of you, you might be working on this through the holidays and just making sure that we get a little bit ahead. But we haven't done necessarily the trig unit. So if you haven't done topic 2 on trigonometry, then this is not going to quite make sense because you need to be aware of the additive rule within trigonometry. But I'm going to take you through it anyway. I'll highlight those points. If you haven't seen it before, come back and have a look at this later. Adding, subtracting complex numbers is easier in Cartesian form. We've seen that. Just adding a complex number in Cartesian form is simple. Multiplying and dividing those easier in polar form. In Cartesian form, we have to expand the brackets, bring things together. If they're not nice numbers, it's really tricky. Polar form, though, it's quite simple. And it's not to say it's going to be quicker to convert to polar form, multiply and then convert back. It's probably not. But if you were given the option, you'd take polar form. And the rule is that Z1 is equal to this, Z2 is equal to that. Then Z1, Z2 is equal to, we multiply those two things together. But all we need to do is multiply our modulus values, and that is natural, you can see that. But then if we expand our cis alpha and cis beta, and we get those two brackets there, those two brackets expanded give us this real component and this imaginary component. And it turns out that real component is actually the double angle formula for cos alpha plus beta, which is an additive rule, and the imaginary component is sine alpha plus beta, and so we end up with R1, R2 cis alpha plus beta. So we multiply the moduluses and we add the arguments. So there's our general rule. And so we'll see us lead into this in the next video on Dimorphos theorem, but for now, this little bit here might be a bit of a problem, but I'm sure that you can come back to it once we've done that double angle formula. So let's have a look at example 3. And then we'll be finished. Now, some of these are a bit easier than others. So, first, part A. 3 cis pi on 6 times 4 cis negative pi on 4. Well, we just multiply the arguments. Multiply the moduluses and add the arguments. Cis pi on 6 plus negative pi on 4. And this is equal to 3 times 4 is 12. Cis, if I add those, that's 2 pi on 12 minus 3 pi on 12, so negative pi on 12. Okay, so there's the first one. B, we've got a division. Now division works in exactly the same way, except we do the opposite thing. So this will be equal to 9/4. We divide the moduluses and we subtract the arguments. 2 pi on 3 minus pi on 5. There's not much we can do with that division, so I'll just leave it as 9/4. Cis 2 pi on 3 can be 10 pi on 15. Minus 3 pi on 15 is 7 pi on 15. And that's the best we can do. And then the last one is where it gets interesting. This is quite a complex one to calculate using our previous methods. It takes a bit of time. It's not impossible, and actually it's probably going to be quicker to use that method, expanding brackets and multiplying by the modulus of I. But we can also do it using our polar form representation. So if I just give these numbers 1, 2, 3, then I can go through and work out the polar form in each case. So we'll start with 1, and 1 has an R value equal to the square root of 1 squared plus negative root 3 squared, and that's equal to 2, and a theta value of negative root 3 over 1, but tan inverse. I've not really given myself enough room. So tan inverse of negative root 3 over 1. Now, I have to be quadrant aware here. So it is a 1 in the real and then down root 3. That's where I am. I'm in the fourth quadrant, Q4. So I need a fourth quadrant answer. And actually the calculator is going to give me negative pi on 3, which is my fourth quadrant answer. So I'm happy with that. So that's 1. 1 is 1 minus root 3i is equal to 2 cis negative pi on 3. Okay, and then we've got 2. 2 is r equals the square root of 2 squared plus 2 squared, which equals 2 root 2. And theta is equal to tan inverse of 2 over 2. This is the first quadrant, so it's pretty easy to work out. Tan inverse of 2 root 2 is tan inverse of 1, which is pi on 4. And so therefore 2 plus 2i is equal to 2 root 2 cis pi on 4. And the third one's a bit trickier. We've got to be a little bit more intuitive with the third one, because we're dealing with I. So firstly, r is equal to the square root of 1 squared plus 0 squared, which just equals 1. But theta is equal to tan inverse of 1 over 0. And that doesn't work very well, because 1 over 0 obviously blows up in our face when we put it in our calculator. So it turns out this is actually one of our asymptotes for the tan graph. And so if we actually draw the Argand diagram and put I on it, I is 90 degrees around. So the argument for I is 90. Theta equals 90 degrees is fine. We can do that logically. And we can see it's got a modulus of 1 because it's just 1 up the y-axis. But tan of 90 doesn't exist. So if you go back to that tan graph, you're getting something we're going to cover in a trig unit, so you may not have seen it. Tan of 90 doesn't exist. So instead, we can just go straight to I is equal to 1 cis pi on 2, which is 90, or just cis pi on 2. So we bring those answers back into our fraction, and we get 2 cis negative pi on 3 times 2 root 2 cis pi on 4. And then in the denominator we have cis pi on 2. So zooming on this now, we simplify this down to be 2 times 2 root 2 times cis, and I'm going to do my arguments all in one go. Negative pi on 3 plus pi on 4, I'm multiplying there, minus pi on 2 for the denominator. And that's equal to 4 root 2 cis negative pi on 3 becomes negative 4 pi on 12 plus 3 pi on 12 makes negative pi on 12 minus 6 pi on 12 gives me negative 7 pi on 12. So there's 4 root 2 cis negative 7 pi on 12. So you can see this, the build-up took a while for 1, 2, and 3, but then once we get to that build-up, the simplification is quite easy. And I could convert this back into a Cartesian polar form coordinate or Argand form, but in this case I'll leave it for you to do that if you need to. So that's it for polar form and using polar form arithmetic. All the best.